Hello everyone. In this video, we continue with the UDD fractional age assumption. In the previous video, we covered this expression under the UDD assumption where x is an integer and s is between 0 and 1. And now we continue with spx plus t and sqx plus t. And here we assume that s plus t is between 0 and 1. X is an integer. And of course, we assume both s and t are greater than or equal to 0. To get the expression for that, we will apply the previous result where s is between 0 and 1 for the expression of spx, sqx, and lx plus s. All right, x is an integer and s plus t is between 0 and 1. The expression for sqx plus t, rewrite it as 1 minus p. And then the expression for spx plus t can be rewritten as conditional probability. An individual at age x can survive beyond age x plus s plus t, given that the individual already survived up to age x plus t. Here, both t and s plus t is between 0 and 1, so we can adopt the expression here. S plus tpx equals 1 minus s plus t times qx, and tpx is 1 minus t times qx. Upon simplification, we get the expression for sqx plus t here, which is s times qx over 1 minus t times qx. To work with the life table function, instead of working with p's, we can work with the l's. This expression can be expressed as 1 minus lx plus s plus t over lx plus t. And then both t and s plus t are less than or equals 1, then we can adopt this expression analog to the one we have shown above. And we get the expression in terms of the L's and the D's. Sqx plus t equals s times dx over Lx minus t times dx. And if you take the first expression on both the numerator and the denominator multiplied by Lx, then you get the expression below. All right, so we have this expression. Okay, make use of this expression with an example. Given that Q80 is 0.04, calculate 0.6 Q80.1 under UDD assumption. All right, directly make use of the fact that both S and T is between 0 and 1. So here S, the duration part, is 0.6. And then T, the fractional age after age 80 is 0.1. Directly apply the expression here. So we already get the value for S, the T, and X is 80. Q80 is 0.04. Upon substitution, we get the desired result, 0.0241. Alternatively, okay, make use of the conditional probability. 0.6 Q80.1 equals 1 minus 0.6 P80.1, and then express this P as 0.7 P80 over 0.1 P80. S is between 0 and 1. For both numerator, S is 0.7, and denominator, S is 0.1. And then we can make use of this expression. SPX equals 1 minus S times QX. Upon substitution, and of course, we should get the same numerical answer. All right, so we get the second part done. And then the last case, the expression for t plus spx as well as t plus sqx, where x and t are integers and s is between 0 and 1. That is, the duration is more than 1 year. All right, so here we get an expression for t plus spx. We can factor this as tpx times spx plus t. This t is an integer, so x plus t is also an integer. So here we are working with integral ages. Because of the fact that, okay, spx equals 1 minus s times qx, where s is between 0 and 1, as in this case, and therefore this spx plus t is 1 minus s times qx plus t. And if you have this information, the p's and the q's, then you can make use of this information. Or else then we can factor that out. The last term here, tpx times qx plus t, we can rewrite it as tpx minus t plus 1px. And then upon some manipulation, we get an interpolation formula. 1 minus s times tpx plus s times t plus 1px. And this is the expression for t plus spx. T plus spx corresponds to the ages at age x plus t plus s, which is between the ages t and t plus 1. So we make use of this interpolation of the two ages, tpx and t plus 1px, and then we can get t plus spx. And the tpx and the t plus 1px can be expressed in terms of L. So we get an interpolation formula in terms of L. So we have 1 minus s times L x plus t plus s times L x plus t plus 1 over Lx. All right, so it depends on the information provided in the question, then you apply the appropriate formula for the calculation. All right, so let's take a look at an example. Given this mortality table, calculate the value of 2.7 P79.6 under the UDD assumption. All right, so here I express this as 0.4 P79.6 times 2.3 P80, and then express the first P as the conditional probability. The probability that an individual at age 79 can survive up to age 80, provided that this individual can survive up to age 79.6. And then the second term, 2.3 P80, I express this as 2P80 times 0.3 P82. All right, with the non-integral duration, the 0.6 P79 and 0.3 P82 make use of the expression, which is 1 minus s times qx. And then we get this. We get all the q's, q79, 0.02, q82, 0.1. And then we can also get the information related to the p's, which is 1 minus the respective q's. All right, so P79 is 1 minus 0.02, so we get 0.98. Similarly, we get P80, 0.96, and P81, 0.93. Upon calculation, we get the answer, 0.8590. Okay, let's rework this example again using the interpolation formula. All right, so express this as 3.3 P79 over 0.6 P79. An individual can survive up to age 82.3, currently at age 79, given that this individual already survived to age 79.6. The interpolation formula. All right, 3.3 P79. So the corresponding age is 82.3. So that is, we are dealing with the fractional ages between age 82 and 83. So we have T equals 3. The interpolation formula for P, 3P79 and 4P79, S is 0.3. So we have the expression in the numerator, and in the denominator, we simply use the expression for SPX, where S is between 0 and 1. So we have 1 minus S, which is 0.6 times Q79. We need to get the value for 3P79 and 4P79, but it is easy to do so because we are given the QX for integral ages. So we have 3P79, which is P79, which is 1 minus 0.02 times P80 and P81. So take 1 minus 0.04 and 1 minus 0.07 respectively. We get the value for the P's. And then similarly, we get the value for 4P79 by multiplying these 4 P's together. Upon calculation, we should get the same answer as well, 0.8590. All right, that's it for today's video. In the next video, I'll give you more examples using the live table functions. Thank you, and see you in the next video.